Okay, first of all, thanks to coming to Milwaukee. Right, that's great, and actually, I think it's the first conference we have in this building. As you probably know, this is a very new building. Of course, we are very excited, and I hope you are excited too. But not only about the building, but also about the workshop, right? So, let me start with manifold embedding. This manifold embedding part 1. So the title is From Single Particle Snapshots to Movies of Molecular Machines and Energy Landscape. So that looks very promising. And whoops, no, I need to see if this works. Next. Okay. So first, outline. First of all, why the hell single particle methods? We have crystals, and many of you worked in single crystal, nanocrystal structure retrieval, and it's very, very promising, actually, very excellent result. So why single particle methods? That's the first question. Then manifold embedding. I will show a little bit. I think most people are not familiar with I don't go to topological spaces. Fortunately, I'm actually not a mathematician, so I have a pretty pragmatic view about these things, so sorry. And then I apply this manifold technique to identical particles, first with no object symmetry, and then with object symmetry, so we can deal with something like an icosahedron, for example. And most interesting are the non-identical particles. When we have conformations, and these conformations can be discrete, several distinct classes, or they can be continuous. And probably this is the most, maybe the message that we can potentially use manifold embedding for these continuous conformations. Okay, first of all, I start with a phrase from Peter Moore, which was a few years ago. I just read it, has been slightly paraphrased. The golden age of structure determination is drawing to a close, with the focus shifting towards structural changes. During functions in the future, kinetics and thermodynamics will become increasingly important, and we'll have to think about dynamics far more careful than in the past. But that's important things. Structural changes during function, kinetics, thermodynamics, and dynamics.
Who's Peter Moore?
This is a...
Watson.
Yeah. Yes, he wrote this nice video. He's a biophysicist. Right. Actually, I don't. He's retired now. I don't know. Maybe you know where he was at Yale. Yes, and so thank you. Yeah. Okay. So first of all, why single particle methods other than not need crystals? Of course, single particle. If you cannot make a crystal, probably not a crystal at all, not even a nanocrystal. Probably a single particle is the only choice, or maybe solutions. That's also another way. But I want to go beyond that, not just the idea that we don't need crystals. Well, there are pretty good reasons for that, because during a function of a molecule will go through many different conformational changes. For example, molecular machines, viruses, when they infect in the host cell. If we have this conformational heterogeneity, then this precludes averaging. We cannot just average all the particles together, because when we do that, we get the blurry image. We lose resolution by averaging. Of course, when we do crystals, as Marius, for example, it's reasonable to freeze in conformations. But I'm talking about the case where we want to look at an ensemble of particles which are in different conformations, not frozen in. And of course, these conformational changes can be either discrete or continuous. And the distinction between discrete and continuous is probably more like a matter of sampling and signal-to-noise ratio. Now, the single particle methods are, of course, ideally suited to study this conformation, because each snapshot represents a molecule in exactly one state point. Right? That is the idea. And today, we are all in the X file, which we know we can do single particles with X-rays, but if we talk about single particle methods, there's another method which you probably know. This is the well-established cryo-EM microscopy. And we always have to compare our X-file single particle methods with the one from X-file to the one from cryo-EM. There's no other way. As I will show, the cryo-EM has now the lead, but we will keep up. Right. So as you probably know, cryo-EM, we use an electron microscope. We, instead of a diffraction pattern, we obtain an image. It's a real space image. It's a projection about particles, about the single particles that are embedded in vitreous eyes. We have fancy electron optics, and basically we can then see individual particles. Also, it's extremely noisy. I'm not sure if you can see it from this distance. I can hardly see the particles. We have a low contrast. We have low contrast noisy images. And of course, conformation is unknown. And also the orientation, it's a projection. Single particles are in random orientations. That's the goal, to retrieve at the end the structure of each component. This is probably almost too repetitive, but there's maybe some other people who haven't seen that. The X-file uses an ultra-short X-ray pulse to obtain a diffraction pattern. And what we obtain, contrary to electron microscopy, where we get many images, many snapshots in one image, we can isolate them. We can select them out in single particle X-file. We need to hit a single molecule. If we have multiple molecules, that creates another diffraction pattern. It's also an interesting technique. Milano will talk about multi-particle diffraction. But here, a single particle assumes that we have exactly one particle in the beam. And so, you know, after that, the beam, the X-ray pulse destroys the particle, then it's gone. But before, we have a diffraction pattern of the undisturbed particle. Similar to the okay. Thanks. Okay. So similar to the electron microscopy, of course, the particle orientation and conformation is unknown when you take the diffraction pattern. So what are the single particle challenges? First of all, each snapshot is a 2D projection of a 3D molecule, orientation, conformation unknown. Each molecule is observed only once. It's destroyed after exposure. We cannot use it and maybe look it in another orientation. That's not possible. Snapshots are very noisy, in particular for electron microscopy, but also for X-rays at very high resolution. Now, historically, most data reconstruction algorithms assume identical molecules. It's just because it's easier. But then we ruin the complete advantage of single particle methods, so that we could potentially, with single particle methods, we don't need to average over unlike particles. So we need a data analysis approach. And what we developed here at UWM during the last couple of years is actually a manifold embedding technique. And first, I start with the results. Actually, the results have been obtained from single particle cryo-EM snapshots. So we have a bunch of snapshots which look like this, and it's you need already software to find out that here's a particle, because it's so noisy. And we take roughly 1 million of these snapshots, and at the end we get, what do we get out? Well, we get 3-dimensional structure of a ribosome. Actually, this has been obtained by manifold embedding. And we can see the conformations. So now this is a movie. You see here the ribosome in 3 different views. Ali will talk about this much more in details in the second talk. But on the right-hand side, we have the energy landscape. And see the energy landscape as this triangular form. And the blue regions are regions of low energy. It's here in energy kilocalories per mole. And when we go along this path of lowest energy, we see the conformational changes of the ribosome. So we have 3 structural retrievement. We have conformations as a function. Now be careful. Is it a function of time? Not really. It's not time what we see here, but it's along the path of low energies. This actually has been obtained from cryo-EM data from Joachim Frank in Colombia. And it actually, when we compare these conformational changes from the 3-dimensional reconstruction, we can actually relate this to the elongation cycle of a translated ribosome.
What is missing, of course, is the structural interpretation.
Well, this can be done. Yes, yeah. But yes, but Ali will talk about that ribosome in more detail. I don't at the moment time is to go into that. So let me briefly go into manifold embedding, because it's also when we give talks at conferences, we normally don't talk about this, about the details, and I want to highlight this a little bit, and so you can also use the technique, right? So what is manifold embedding? Well, first what we have is a data set. And in the data set, we have normally images or diffraction patterns, and they have pixels. And we can represent each snapshot by a high-dimensional vector of dimension p, where p is just a pixel number. That's just how the data is get from the experiment. And then we can think of making a plot. The plot is not very useful because how many dimensions has this space? It can be 1 million, right? You know how many pixels you have, or for crystals even more, like crazy, right? So, and you cannot really represent that. You wouldn't see nothing. Nevertheless, conceptually, when you have a single particles, and let's first assume that it's always the same particle in different orientations. This intrinsic manifold is only 3 dimensional because we have only 3 degrees of freedom represented by some quaternion orientations, Euler angles, always 3. So in this very high dimensional data space, there's a curved hypersurface which has 3 dimensions, right? If we now have conformations, we add dimensions to it, but we will probably never get to p dimension, right? We don't want to deal with p-dimensional manifolds. This is just the embedding space. The manifold dimensions, of course, are the number of degrees of freedom in the data, and we certainly assume that this dimension is much less than the data space. Now, what does manifold embedding? Basically, the idea is to now represent the whole data, the whole information of this data set in a low-dimensional space. The space, of course, should be much less than the number of pixels. Then the manifold embedding allows to determine the number of degrees of freedom. You do this in an exercise. They give you some test data, you can find out what the dimension is. And the manifold embedding allows then to project each of these data points in this high-dimensional space to the manifold. And this also performs noise reduction, which we need. So we can work at very low signal levels, or if you want low dose for cryo-EM, while it prevents all relevant degrees of freedom, orientations, conformation, maybe other parameters. So there's a whole family or generation for manifold embedding. It's impossible to go through this in details. But for practical reasons, we're actually choosing the so-called diffusion map. The diffusion map is based on graph theory using similarity between snapshots, and it has been established by Koifman and Lafont. This is really the paper if you want to understand the mathematical details. That's the right paper to start with. And I simplified this a little bit, but I want to give you at least an idea. So, diffusion map. So it's based on a graph, right? And what we have, a graph, you know, are points, and they are connected with some links, and the links are weights. I can think that are a few data points here, 6 data points. And we now introduce a similarity between these snapshots. The similarity is just the Euclidean distance. That would be the Euclidean distance in this high-dimensional data space divided by some sigma parameter. This is a weight, and we put this distance actually into an exponential, which means if sigma is very small, if the distance gets large, it immediately drops down. So basically, this formulation of similarity just looks at the very local neighborhood of the data points. That's what we do. And then we have this similarity, and actually we can do a small trick. We can basically, if we divide the similarity Kij by the sum of the similarities for one data point, then we can normalize this. And Pij is a probability. That's the probability that basically a point from here would end up here after one time step.
Could you comment on the Euclidean distance? How do you calculate that?
Euclidean distance is just, you know, the Pythagoras. Maybe we just check the difference between the points, the lengths between the points.
So how do you calculate this? You have two vectors, right?
Yes, yeah.
One diffraction pattern and another diffraction pattern.
Yes,
how do you calculate it?
Okay.
I think the people are might be interested in that.
Okay.
Great.
So you have, let's say, A and B. Okay. So if it's in 2 dimensions, of course, it's just these components. So the square, we take the square root of that, that's the difference. And then for higher dimensions, you just add this for each component.
Here, squares outside of bracket.
I'm sorry, yes, yeah, that's outside the bracket. Yes. So but inside the sum, yeah. Okay. This is the Euclidean distance. Thanks for the question. So please ask if you have some questions. So by this normalization, we can actually obtain a probability. And this now we can interpret these weights, if you want, as a Markov process. That's essentially like you can think random walk, Brownian motion. Right, there's a start from here, and we have a transition probability from this point to this point, and so on. At the end, of course, the particle will, the probability that it goes to some place in total will be 100%. So now,
what does each point in that diagram represent?
This is essentially
a single pixel, or is it
it's a snapshot. It's a snapshot.
Whole snapshot.
Yes, right? It's a snapshot. Yeah. Then now from the, without going to the theory of the Markov processes, we can repeat this if we multiply this transition for one time step with itself n times. That gives the probability of a transition from between 2 points after t time steps. Right? So now we have a random walk on this graph. And if we have shorter times, small t's, then we reveal only the local geometry of this graph.
So that is done only for one snapshot, and then for the next snapshot.
This is done for the whole snapshot. This is for all pairs.
But then each snapshot is compared to all the snapshots.
Yes, very important. Yes. All pairs. We take it's very important. All the complete information in the data set, which is all similarities. But this weight we use is very narrow. It's very narrow because it decays. So we call this also the kernel is very localized. That's why at small time steps, for small time steps, you have only local information of the data. So, but it's clear if we repeat this Markov process many times, then we see more of the global manifold, because we can think actually of diffusion. That's why it's called diffusion map, in a nutshell, right? We can see, for example, if I have a cloud of point here, like this shape here, we can think of a green path that will be very unlikely, because there's a very unlikely hopping probability across the path where there's no data. So the red path is favored. And it also means that actually we introduce something which is called the diffusion distance. And this is actually related to the connectivity. Whenever we have a lot of data points linked together with high weights, high probability, we have a large connectivity. That's why this diffusion distance is actually a measure of the connectivity. And if we progress our diffusion on the manifold, the points along when we have data not connected appear closer than others. So the diffusion is a measure of the distance along the data structure, and not just in the beginning like the Euclidean distance between the two points.
Just a question. I think that what you have is ik minus jk.
Yeah, yeah. So you can, it's not so probably immediately to see, but you can see if you have high probabilities here, which are all very similar, this diffusion distance becomes smaller. Right, let's see. But if you now look at this diffusion distance, we would like, of course, to calculate this. We realize that's actually quite costly, because we have to take the transition matrix, which has n times n points. N is about, let's say, 1,000,000 typically. You have to do this t times. That would be a costly task. But we use a trick. So again, simplified a little bit. It's actually, we can also represent actually this diffusion distance first, also in a new Euclidean space. Not the Euclidean space of the data, but the Euclidean space of the diffusion distance. And of course, the diffusion distance is exactly the same as this, but not now with the data points, but with the transition probabilities. Then we can write this new space with a y for each particle as a function of time with the transition probability. And the trick is now, of course, when you have powers of this probability matrix, that's a costly calculation. But if you calculate the eigenvectors, it's very simple. Right? So we basically transform these probabilities into their eigenvector representation. And then after iteration of these probabilities, they stay the same. And just the eigenvalues get the power of t. And then we can actually, the eigenvectors of this probability matrix, we can order them, and the decay, of course, of these eigenvectors depends on the value of lambda. And small, actually lambda can show that there is proper normalization is smaller than 1. So for a larger time, only what we call the dominant eigenvectors will survive. And that is exactly how we can represent the data in low-dimensional space by diffusion map technique. So that's not the whole thing. That's the first important thing. The second important thing is that we have a mathematical link to the Riemannian geometry. What is a Riemannian geometry? Essentially, this is a manifold which can be curved, like, for example, a sphere, plus a way to measure distances on this manifold. You probably know that this can be represented by this quadratic form, which is actually which can calculate the line element on a manifold, and then this is used in general relativity, where you have curved spaces, and there's a way to calculate, because now the geometry changes or can change from point to point. In an Euclidean space, this Gij, I'm using here the Einstein convention, not using the double sum, would be constant, but that's not necessarily the case. And then you can also define, that looks ugly, I'm sorry, but that's the way it is. But you can see, I know everybody can figure it out easily, maybe after the workshop. We can define also a Laplace-Beltrami operator on the manifold. That's if you use that, if the metric G is just a diagonal, then you see this is just a conventional Laplacian operator. But if it's in a curved manifold, we have to take the metric into account. The important thing is that when we know the metric, we can determine the eigenfunctions, at least in principle. Not always analytically, but they are entirely defined by the metric, nothing else. And the fantastic thing is that the diffusion map approximates the so-called Laplace-Beltrami operator on the manifold. So we have a continuous manifold, which is represented by a Riemannian metric, and we have our data points, our measurements, and we have a link between diffusion map, the results of diffusion map, and the Laplace-Beltrami operator. And the thing you have to remember, and that's maybe the most important thing, because these things are not easy to understand. They are not easy to understand for me either, even now. But the thing you can remember, and that helps, that the diffusion map eigenvectors are the eigenfunctions of the Laplace-Beltrami operator sampled at the snapshots. You remember that, you're in a good shape. And also, you know, in this Laplace-Beltrami operator, you have also bounds. Manifold can be bounded, not all. Some are unbounded, like a circle or a sphere. But for bounded manifolds, you need to take the Neumann boundary condition, where the derivative is 0. Okay. Now, I'll just do a simple example. You have more examples in your exercises, and actually that shows a little bit the also an important feature of this diffusion map. On the left-hand side, we see different manifolds. Actually, these are only in 3 dimensions. Otherwise, I cannot really plot it. Right? But so it's 3 dimensions. But if you look at these manifolds, which is a closed curve, they look quite different. Especially in the projections. If you think that the projection, they intersect at many points. So if you see that, it's not immediately even obvious that is a closed curve, right? But now if you do the magic trick of manifold embedding, they end up all like this, a circle, independent of how they are represented in the data space, because the eigenfunctions only depend on the metric, and the metric is a property on the manifold, on this how we measure lengths on a curve. And that's very easy. This is just the arc length. The arc length is just a parameterization of this curve. I'm going to into the mathematics. The Laplace-Beltrami operator for this one-dimensional manifold is, of course, just the second derivative of the curve here. And you know, what are the eigenfunctions? These are sine and cos functions. And we don't have bounds. It's a circle. So regardless of how the data is represented in data space, we end up all with the same curve, which is easy to interpret. We can find out, we immediately see what the neighborhood of the points look like, unlike the data space, where it's highly intersecting. So that's one of the key features, and you will see that in practical examples this afternoon. So I'm sure many of you heard about principal component analysis, and often, you know, the question is, what is the difference? Right? So there's a difference in principal component analysis. You basically describe the data as an ellipsoid along some principal axes. It has no information about the intrinsically dimensionality of the manifold. Let's assume we have a curve. Then we, like the example we had before, they have something like this. Basically, the PCA gives a space which represents the volume, essentially, of this curve. But there's no information about the dimension. That's what we need. That's what we need for analysis. So in we have one exception. If the space is already linear, a plane, and they, of course, are equivalent. But normally it's not. And the typical example is the jelly roll. So actually, I don't call this Swiss roll because I'm Swiss and we don't have Swiss rolls in Switzerland. That's why I call it jelly roll. That's a classical example. That's a wrapped sheet, essentially a wrapped sheet. And if you do principal component analysis, your distances on the manifold will be from here to here. So this data, this path will go through the manifold, which is empty. There's nothing there. What we want is a measure of a distance between these 2 points, which is measured on the manifold along the connectivity of the path. So that's the difference between and there are other flavors, and diffusion map has also different kinds of we call this kernels, variety of kernels, but that's not so important at the moment. So, a summary of the manifold embedding. Manifold embedding is a low-dimensional representation of the data space, and the manifold diffusion distance is actually represented in a new Euclidean space with the lowest possible dimensions, much less than you have number of pixels. Preserves the degrees of freedom, such as orientation, conformation, and so on. Performs noise reduction, so we can deal with low levels. And also important, we do not need templates. We don't need any templates or putting prior information. We can do an analysis just from a data as it comes from the experiment. And also we have a mathematically sound way with diffusion map because we have a link to the Laplacian eigenfunctions of the manifold because the diffusion map eigenvectors are the eigenfunctions sampled at the snapshot points. And further, and that's also important, diffusion map is computationally cheap because we only basically need to calculate the Euclidean distance. That's maybe not so cheap if you have millions of snapshots, but it can be done in a few hours. And then secondly, the eigenvalue eigenvector problem is easy because it's a sparse matrix and we only need a few eigenvectors to compute. Okay, so first I start with identical particles. before we go to conformations, I go briefly through the identical particles. Also a lot will be presented by Ahmad, so I go through that rather quickly and just show you the main features. Now the question is, I mentioned we have a metric, right? What does the metric mean in the context of diffraction? Because to get an idea of the eigenfunctions, we need an idea of the metric. And this is, I demonstrated at hand with a small simulation. So let's assume we have an object, and we take a diffraction pattern, and I look this in different orientations. While we change the orientation, the diffraction pattern will change. So we can change we can measure or estimate the local change, the change rate. For example, if we rotate the molecule about the x-axis, and G, this is the metric for the rate change when we change about the x-axis, is plotted here. In the middle, you see the change between adjacent snapshots, and you see here the change of the metric. The same for the y-axis and the z-axis. And when you see that is, first of all, the metric doesn't change along the z-axis. Think about it. Well, the diffraction pattern is always the same, right? It's just rotated.
Excess come along.
Yes,
right?
yeah.
So that was a point that bothered me at the very beginning.
Me
When
too.
you define the distance in the first slide. So two snapshots around Z could look very different if you're measuring point by point.
Yes, yeah.
So what would suppose all of the snapshots were the same, but just rotated around Z? What would the diffusion map look like? Would it just be a row of points?
Well, in the embedding space, it would be a circle. Because it's a
360 degrees, yes.
Yes.
And what happens is you have to have enough snapshots that there are ones close to each other.
Yes, yeah,
Okay,
yeah, that's right. Yeah. So yeah, that's right. But here the important point is, you know, what actually I was very worried at the beginning that when you look at what we call the metric induced by scattering for orientation, that could be a very complicated metric. But it's not. First of all, about the z-axis is a constant. About the x and y-axis, the changes are very small. And that is the key. Now we can approximate the metric of induced scattering by a simple metric which is just diagonal form. So two rates for x and y. So G22 is equal to G1 and G3 is 3. And we call this a metric that doesn't depend on the orientation, we call homogeneous. And that turns out to be the case for many scattering and image conditions. So we can write our induced metric by the metric of a homogeneous top plus an object-specific term. And this actually is known, the so-called metric of the symmetric top, has been treated in classical mechanics and quantum mechanics, and just a paper by Hu about this metric in the context of general relativity. And now if you have these metrics, we need just to put this into Laplace-Beltrami operator and get the eigenfunctions out. So I'm not assuming that you're doing that now or even in the future, but I just show you what the results are. So the eigenfunctions are just the Wigner-D functions of rotation. And the Wigner-D function of rotations contain orientational information. And this can be easily retrieved, right? So what is the workflow if we want to recover orientations? First, we calculate the Euclidean distance between the snapshots, come up with our graph, with our weights, set up the diffusion matrix, estimate the eigenvectors and eigenvalues of the diffusion matrix. Then we know they must be equivalent to the Wigner-D functions. We can compare the eigenvectors and find the orientation by a least square fit. So this will be showed in much more detail by Ahmad in the third section. Finally, for getting structural information, you like to have this in real space, right? That's what we want to see. Once we have the orientation, of course, we have an additional step. We need to reconstruct the three-dimensional diffraction volume. That's the first thing. And as we know, phases are lost in diffraction. There's an additional step needed. So we have the so-called phase problem of X-ray crystallography. And single particles, this is a bit different because we don't have Bragg peaks. If we don't have Bragg peaks, it's actually possible to retrieve the electron density by iterative phasing. And that's what we use. Don't go to the details. Algorithms based on charge flipping or shrink wrap, then we can get something out of like this. This is a ADK molecule, which this is from a simulation, which we retrieved from this manifold embedding technique, and this is the electron density, and inside you see the model from the PEB file. So let's also check that our method works.
So how many snapshots did you use?
Yeah, that's a very good question. Actually, in that case, we used about 2 million. 2 billion? 2 million. Yeah. So actually, the number of snapshots is related to what is called the number of resolution elements. The number of resolution elements is just defined by the object diameter divided by the resolution, and that is in that case 30. Yeah. So how many minutes? So it's almost through. Okay. Yeah. I don't need to go through that in very much detail. Ahmad will tell us about the object symmetry. If you have, just briefly, if you have object symmetry, of course, the Wigley function will also have the same object symmetry. So we can basically symmetrize our Wigley function. That will be presented by Ahmad, and then we can do these things. We had actually 2 angstrom resolution of an SDNV. That case also simulated data where you get 100 resolution. It's about 1 million snapshots in that case because we have symmetry, don't need that many. Then, of course, the most important thing which will be actually covered by Ali just now is the conformational changes. And just very briefly, if we augment now our idea of having the eigenfunctions from orientations, what is about conformations? So if we get the manifold of conformation, we first have to deal with an orientational change and the conformational change. So our manifold will have a larger dimension, and of course the key question is, can we separate orientations from conformation? And that's not so easy to do because now we need to learn how to navigate on the manifold. It's a surface, but where is the orientation as the conformation? There are simple cases. If you have also homogeneous form, that is easy to do because this metric, the Laplacian, would separate into eigenfunctions of pure orientations and pure eigenfunctions of conformation. And that can work in some cases. It's a simulation also of ADK with different conformations, which are here continuous, and you basically see this two-dimensional 2, which gives you first the orientation. This is just a single orientation about the single axis. It's highly simplified. This is the conformational change. But the conformational change in that case is relatively large. So that's why this works in that case. It's very different from the ribosome. For example, take a ribosome, then these are 2 ribosomes in the same orientation, and then a conformational change. And it's really hard to see. It's almost impossible to see that there's a difference. And it's even worse. In cryo-EM, it looks like this. It's completely noisy. So the conformational signal is very small. The orientations dominate. And we have other complications like the microscope transfer function, which I don't need to go into detail. But before I hand it over then to Ali, actually we have done the discussion first. I just want to show you briefly how we deal with that. Now I said the orientations dominate the manifold. This is looks like a disadvantage, but it's also an advantage because since the orientations dominate, we can orient the snapshots all together. We can ignore the conformation change. And then what we do, we analyze conformations of the snapshots in very nearby orientations, or better called projection distance, using the known orientations. And this allows then to separate conformation from orientation. But I think I stop here because otherwise I just have too much redundancy with Ali, which will go through the whole workflow, which is not easy to do. But the workflow has been used to get this beautiful movie I showed at the beginning of the talk. And I hope you have now a little bit a better understanding of this mysterious manifold embedding. Thank you.